Hello everyone, I'm Sojong Kim, and this time we are going to solve the ILP problem using branch-bound algorithm. And here is a problem. So we want to maximize this objective function involving these four constraints using branch-bound. Particularly, I'm going to use Excel to solve this problem. So open your Excel file so that you can use a solver in your Excel to solve this problem. And here, yes, easily you can just use a solver to get the solution, but this time we are going to use you have to use a branch bound algorithm. So first of all, let's solve. You have to eliminate the linear condition constraint because that's the first step of the branch bound algorithm. So initially, branch bound algorithm found the solution from the LP model. Okay, so let's solve the problem. We have two decision variables, which is x1 and x2. Okay, and then we have constraint. So associate with the x1 and s2, and their coefficient will be 6, 4 for the first one. Let me make this table to solve the problem easily. Okay, this is a less than, so less than 24. So you can use the sum product function to get the left hand side of the inequality. So first of all, you have to select the values of the decision variable and then select the coefficient associated in the first equation. So this is and by the way, when you reference the decision variables, you have to use absolute reference so that you can use autofill function later, something like this. Okay, anyway, and second constraint coefficient is 1, 2, and then these are the total will be less than left hand side of this inequality is less than 6. You can use autofill function in Excel. So that's it. That's for the first initial step. I mean the first iteration of the branch bound algorithm. And we have objective function involving two decision variables with their coefficient. So total will be currently 0 because we have 0 here. Got it? However, if you type any number here, then definitely you can get some values. So initially, let's say these are the 0. Okay, let's use a solver. So if you don't have solver, you can go to option, and there is add-in so that you can add the solver, okay, into your Excel. But in my case, I already have one, so I can just click the this solver to get the solution. Once again, we want to maximize this objective function, and by changing the values of these two variables and add a constraint. So these two numbers should be less than their the values in the right hand side. So where are you? Okay, these two, and click OK. Got it? And then yes, it uses simplex LP so that we can get the solution for the first one. So this is the first iteration, result of the first iteration in branch bound algorithm. So what's the issue? Unfortunately, x2 has a real number, right? So originally, if you look at the original problem, it's integer linear programming. So all variable must have the integer, not real number. So definitely we have to consider the closest integers to this 1.5, which is 2, either 2 or 3. No, either 1 or 2, right? So because this is between 1 and 2, so 1 can be the one constraint for the next iteration, and then it can be used as a constraint for the third iteration. So here LP1, give the solution of the LP1 was 21, but when x1 equal to 3 and x2 equal to 1.5. And then each of the object function of the first iteration is 21. So what's the next? Here, if you look at it, this is infeasible solution because x2 has a real number, not the integer. In this case, as I mentioned before, you should check in branch bio algorithm, you should check the closest integer to this 1.5. So next LP2, in LP2, you should add this constraint because 1.5 is between 1 and 2. So first one, lower bound, so x2 can be less than or equal to 1 so that it can be 1, and x2 also can be greater than or equal to 2 so that it can be 2 in LP3. Got it? So let's solve these two models. In fact, I already got a solution for you. So LP2 and LP3. So if you look at it, check it, and then here I just add one more constraint here from the LP1 model. So in LP1 we have only two constraints given by this problem because the LP1 does not include the integer constraint. So that you can find the solution from the LP model. And next we add one more constraint here in LP2. So x2 is less than equal to 1, right? And here if you have this constraint, then you can get this solution. So x1, so z value, which is objective value, will be about 20.7 when x1 equal to 3.3, x2 equal to, and x2 equals to 1. Okay, so here, but unfortunately because x1 has a real number, so it cannot be feasible. So we got infeasible solution here. So you need to do more from this LP2 model. However, LP3, instead of this constraint, we say that in this case LP3 has this constraint. So x2 is greater than and equals to 2. Okay, just be careful about this inequality. Third constraint has a different inequality. And if you use a solver to get the solution, then z value will be 18 when x1 equals 2 and x2 equals 2. So here you can check whether they are integer or not. Here, because they are integers, so we got the feasible solution. Got it? Although problem just asks us to consider the first three RP models, but let's consider more because I want to check the all possible solution. So what can in LP4, which will start from the LP2, you have to add one more constraint, associate x1. X1 is what? Is less than or equal to 3 because 3 is the closest integer to the 3.3, right? So here, yes, it must be 1 so that you can find the solution. And we also need to consider another LP model, which is LP5. And in this case, LP5 will be in LP5 x2 still equal to less than equals to 1, and however x1 should be greater than and equals to 4 so that x1 can be 4, right? Can have an integer value. So let's look at x4 and x5. Okay, x3, no, LP4. Let me create LP4. So in this time, yes, we will make a one new worksheet together. So here, let me just copy and paste the existing LP model. So here, x2, it should be less than equal to 1 in LP4. Also, we need one more constraint, associate x1, and basically the x1 should be less than equal to 3. And you can use just autofill function from the previous cell. So we have 4 different constraints here, and then once you have 4 different constraints, you can use a solver. So click solver, maximize this the object function. Here's the max by changing these two values of these two variables, and add the constraint saying that left hand side is always is less than equals to the values of right hand side, and we are going to use a simplex because branch bound are going to use a simplex. So in this case we got 19. G value is 19 when x1 equals to 3, x2 equals to 1, right? So here, you should check the values of two different variables, and here they are integers, so it is feasible solution. And what about the last one? We cannot stop it because we have to consider the all possible cases. So let's consider alpha 5, and each way is that you can just copy and paste the previous Excel worksheet. So here we have but in here we have one different constraint here, so this one should be greater than equals to 4, right? So in server we have to update the server, right? So here, yes, we want to maximize this objective function, and by changing the values of two decision variables and add a constraint here. So you should check the sign of these four equalities. So first three, the value in first three should be less than equals to equal to right hand side of their right hand side, and this one is greater than equal to 4. Okay, so we have two different constraints, and using simplex LP, so click solve so that you can get the solution. So we got 20 when x1 equals 4 and x2 equals 0. Also, it is a feasible solution because two variables are integer. So we are done actually, because we already checked all possible cases in branch bound algorithm, right? And so far we have 5 different LP models. So if you draw the branch bound tree, then you can get the answer of the first sub question. Okay, let me just use a PowerPoint. So here, this is the first LP, and so if you press F2, you can type the text in the box. Okay, and these are too small, so I can just change the shape. And next one is LP. The first one is LP1, I'm sorry, and this is LP2, and we have LP3. We have with different number, so you should type the solution of each LP model. So that you can just develop the tree, branch bound tree. And this is 2, this was 2, 18. However, we have two more models here and there, and which is LP4, and this is LP5, and LP4. What's the solution? This is 3, 1, 3, 1, 19, and this is 4, 0, 20. Insert arrow, so that you can check which model came from where. Okay, and then we have to add constraint. Sorry, so constraint here. So initially x2 was less than equal to 2, no, 1, and this one x2 is greater than equal to 2, and here LP4 we oh yes, here we add another constraint associate x1, so is a less than x1 is less than equals to 3 and greater than equals to 4. Oops, not 40. Okay, so here's 4. So finally we got the solution of the oops RP model. So this is a branch bound tree, and also if you possible you can write down the feasibility of the solution, and if you look at it, which one is optimum solution? Last one, right? LP5. So far we have 3 feasible solution, and out of the 3 you have the one optimum solution. Okay, this is end of the first problem, I guess. I solved problem. Then let's solve the next sub. Let's answer the next sub question. So here, so we have this sub question. Provide your final solution with each ILP model. So what's the definition of model? RP model include object function and their constraint, right? Plus, yes, if it's possible, you can provide definition of decision variables, but here we already the initially ILP model is given, so you can just use this one to answer the next sub question. Got it? And however, this cannot be the answer because based on your this branch bound tree, and your optimum solution is given by the last one, so you should add 2 more constraints into your solution. X2 less than equal to, oh sorry, 1, and x1 is greater than equals to 4. Oh, sequence doesn't not matter. 4. Alrighty, so here also ask, so final solution, we also need to write down the final solution. So this one will be the optimum solution. Okay, so this will be the final answer. However, in this problem, if you go back to your problem, basically initially it ask you check the first 3 LP models. So another solution is that you can actually the original solution should be the answer. You should get the answer from these by considering only these first 3, like the model, which is not the optimum. But here if you look at it, there is one feasible solution. So based on this first sub question, and basically you can just give me RP3, because according to the problem you don't need to consider these other two RP models. But originally if you use a branch bound tree, and then definitely yes, the last one is the optimum solution. But because this problem asks you to consider the first 3 RP model and then select the best solution from the 3, so it will be the RP3. Okay, so if you write down LP3 instead of LP5, then LP3 is x2 is greater than equal to, so LP3, LP3, LP3. So LP3 and with different constraint. So initially this is greater than equals to 2, I guess. So LP, you should provide solution and LP model involving objective function and their its constraint. So that's a solution of this problem.